if you recall, the patch number C of a surface length is the smallest C such that S admits a piece of bridge trisection with C sub I equals C for one of the parameters I. And what we saw last time is that this patch number is bounded above by the original rank. So we have a sequence of inequalities. We have the rank of the fundamental group of the not exterior is definitely smaller and no larger than the original rank of this group. Which is bounded below by the patch number, or bounded above by the patch number. The patch number is bounded below. Okay. So in particular, if S admits a B1 bridge trisection, then I1 of the surface length group is cyclic. Okay. And then maybe I'll just note that H1 of S4 minus S is congruent to either Z, in the connected case, Z or Z mod 2 if S is connected and orientable, and if S is connected and okay. And so maybe as an exercise, I don't know, maybe this is something you've already done. Perhaps you've computed that pi1 of S4 minus, say, these unknotted surfaces Pij is simply Z mod 2. Whereas, say, pi1 of an unknotted orientable surface is going to be Z. Okay, so this is sort of the place we find ourselves, and there's been a lot of interest in trying to understand what it means for a surface length, or in this case, it would be a surface knot, because if the group has rank 1, if the group is cyclic, it has to be connected. What it means for a surface knot to have such a group. So this brings us to what's known as the unknotting conjecture. Which states that if I1 of S4 minus S is cyclic, then S is unknotted. Okay, so there's been some progress on this conjecture. Friedman's work on topological four manifolds, that's 82, tells us that this is true. True in the topological category for surface knots that are for two knots. Remember, this means that S is homeomorphic to S. Okay. And shortly after that, we have a result of Lawson, which pushes this to projective planes. So it's also true in the topological category for those surface knots that are homeomorphic to RP2. So these results use topological surgery. And then there's a sequence of results by Kawauchi and Hillman. Maybe I'll just say CF Kawauchi in 2013. The original papers had some errors in them. There was a sequence of papers that were posted that supposedly fixed the errors. My understanding from talking to people is that it's not totally clear whether these results are fully established, but they've been published, so I think we should probably give them the benefit of the doubt. And these say that this is true in the topological category for S orientable. So if you've got, and so let me maybe just say a little bit about what true in the topological category means. I like to think about what unknotted means. So unknotted you can think of as meaning the surface knot is isotopic to the standard, the embedded surface knot, right? Or isotopic, say in this case, into S3. And so what these results are saying is that such an isotopy exists, but the isotopy may not be smooth at all points. So you can start with a smoothly embedded surface. If its group is cyclic, there's an isotopy through totally flat, topologically flat embedded surfaces, taking it to the standard sort of unknotted space surface. Okay. So this is kind of what's known. As far as I know, there's no general result about whether this is true for non-orientable surfaces of small or Euler characters, connected sums of particles. I mean, it seems like it's one of those things where maybe all of the machinery is there, but it would be sort of very, very involved to try to promote these results. Okay, does anybody have any questions about that? So there's a nice result that contrasts these in the smooth category. This is the theorem of finishing, Crack, Bureau from 1987. I should say that like sort of the original techniques that were used in here are, due to Friedman. But so for most sort of more advanced topological surgery techniques, there's a machinery called crack surgery, which is, I think,
they don't boil it down to Friedman's results.
Well, everything boils down to Friedman's results, yeah. But for when you have a more like the thing that changes here. So what changes? The thing that changes is the boundary of the knot exterior, and also, I guess, in like this case, the higher homology of the surface thing. So Crack has a sort of more involved machine that takes more things into account. Okay, so what does this result say? This result says there exist surface knots. Let's say, let's write it like this. S square Si with I in N, such that, so it's an infinite family of surface knots such that one, these surface knots are pairwise homeomorphic. Pairwise homeomorphic. Oh, so I should say top. Yeah, homeomorphic. But they're pairwise non-diffeomorphic. So there's no smooth equivalence, provided I is not equal to J. And the last fact is that pi1 of their exteriors is Z mod 2, and each of these guys is homeomorphic to a connected sum of 10 RB2s. And I think the normal, I didn't write it down, the normal low number is 14. 14 or 16. Only one of those is possible, so let's do that one. So this is the first example of what you might call like an exotic surface knot. Or exotic surface knots. In that they're all sort of topologically equivalent, but smoothly distinct. I don't think that they showed, at least not in this result, that they are topologically unknotted.
But you could throw the unknot into that list.
Yeah, but then you may not have part one.
Right.
Yeah. Yeah, exactly. And I don't know if that was later established. I think I asked Craig this once. I think he was maybe able in these examples to show that these are actually topologically unknotted in an ad hoc kind of way. I'm not sure where that is in the literature. I don't think it's in this. And these come from, so where do these come from? These come from I think they're anti-homomorphic. Anti-homomorphic involutions on Dolgachevs, exotic copies of the Dolgachev surface. So there's this infinite list of Dolgachev surfaces. There are closed form manifolds that are all homeomorphic, but pairwise non-diffeomorphic, and they all have an involution which you can trace through. And so they show that the quotient of this involution is S4 with fixed point set given by these surfaces, and they use that to get this rule.
So they have drawn explicit pictures in S4, like banded link diagrams.
They don't give banded link diagrams, but they the way they do describe this as they have, there's a sort of like tangle replacement way of thinking about this, where you cut out a piece of the surface that looks like some discs that are twisted on each other, and you take two discs and you go and you put it in where they're twisting on each other. And from that, it should be possible to draw explicit pictures.
So that's a nice project.
That's a nice project, yeah. Peter and I talked about this, Bill and I talked about this a little bit. And I think we were able to come up with what looked like at least something close to a banded link, or a trigon diagram. And then, or a trigon diagram. Yeah, so this would be a great project to try to understand these guys.
So you think there is a move that gets from one to the other?
I think that's right. Yeah, that's a cut and paste.
That would be good to see in the trigon.
Yeah. So there is a very interesting project here. What else was I going to say about this? They also give families of smaller surfaces, just porous, but they're not able to show they're non-diffeomorphic. So to show they're non-diffeomorphic, they're somehow using these big four manifolds. And so here's a question. I think I remember this one. Oh yeah.
They're not diffeomorphic because if they were, the double branch covers would be, or the branch covers or something.
Yeah.
Would be diffeomorphic.
Yeah. So if it's a torus, then the double branch covers are homeomorphic to S2 cross S2. So, Adam, here's a good list of things to test your invariant.
Your variant only works for applying surfaces.
Well, no, but they can do it for orientable surfaces that are smart. So even a torus, they can do it. So
Short paper. The short paper.
that might be the announcement in the memoirs or
bulletin.
bulletin. Yeah. There's a longer one. Unfortunately. All right. Okay. So So this is kind of what I know about the unknotting conjecture. I think it's an interesting thing to be thinking about, or at least keep in mind. But so what does this mean for bridge trisections? Well, there's a couple of natural questions. So one question is if a surface link admits a B, let's say a BC bridge trisection with one of the CI's equal to 1, let's say C1 equal to 1, because that's equal to 1, must S be smoothly unknotted. Okay. So this is a sort of a weaker question than the unknotting conjecture because this implies cyclic group. But it's also sort of a stronger condition in that it's imposing some geometry on the surface. It's saying that they can be trisected so that there's a single patch in one of the sectors. So we can ask, are there even any interesting bridge trisections of this sort? I think it's a very interesting thing to think about. So then another question which I thought of after Adam's talk is, are any of Saltz's invariants ever non-zero for such either the trisection or the surface, right? So you have invariants that are invariants of the trisection. Maybe there's something you can just see from your machinery that if you know that there's one of the pairs is not. Maybe that can automatically make your invariant 0. Or like with the infinity algebra, like super simple in the case of thing.
I have a question. If
Please.
you have a trisection with C1 equal to 1, can you make that one component unlinked crossing this? I guess yes, you can. Yeah.
Yeah, that's right.
Okay.
Yeah. So
then,
let's draw. I mean, you keep asking about the drawing picture.
well, so then it's like you just have a properly embedded surface in a 4-ball, and remember that thing I was mentioning to you the other day.
Yeah, that's right. So you can consider it as like a ribbon surface. Yeah, you consider it as a ribbon surface for the unknown. That's kind of what you're saying.
Well, it's just like if you cut out that sector where it's embedded in 3 dimensions, you have a properly embedded surface in a 4-ball, and I don't see any reason why that would be easier to study, but it's just interesting.
No, that's right. I mean, I think what you're picking up on is when you can always sort of do that by removing the disks from one sector and looking at a surface filling unlinked. But it's a little bit more compelling when it's connected.
Mm-hmm. Just got one disk.
And in
It's one
particular,
happen. I mean, it's a ghost, right? And this thing is,
well, we have to be a little careful because it might not be a sphere.
all right.
But, right, because in particular, if it's, so let's just look at some examples. If it's actually a balanced beam trisection, then the Euler characteristic of S is 3 minus B, right? So it's not a sphere unless B is 1. But on the other hand, let's see if I can do this on the fly. It's always a good idea, right? You can cook up these parameters. Well, and it's not so. You can cook up these parameters so that C2 plus C3 plus 1 minus B equals 2. And in that case, you really are talking about a ghost. That's right. So this is a special, the ghost, well, a special case of this question is a special case of the question about the ghost spheres, which is certainly what they should be called, if not before. Hence, okay. All right. Okay. Any other questions? So this picture also brings me back to what I talked about sort of mysteriously at the end of the unit on bridge splittings, which is the sort of these wicket groups and these intersections of wicket groups and stuff like that. So just from the picture I've drawn right there, comes the sort of natural question, which maybe I'll because I didn't write down. Oh yeah, I did. Okay. So purely three-dimensional question. For which grades beta in the grade group on 2B letters are the links? So the first link we want to consider is T beta, which is that third guy, right? That's the link we call T beta. It's what happens when you act on the wickets with beta. So the first link is we glue this to T0, the first guy. And the second link is we take T beta and we glue on the second tangle, T infinity. So for which grades are these links both unlinked? Because this is precisely the criterion that tells us that what I've drawn on the board is a bridge trisection and not something else.
That's T infinity, the blue one.
Yeah, so this is T0 and T infinity. And when C1 is 1, we can always assume that's what those are. And you could kind of play this game without requiring C1 to be 1, where, you know, like I said, you can have your second favorite tangle here and run the same program. So, so let's just develop this a little bit. So let's consider the double coset again. So take a wicket group and act on grades on the left coset by the wicket group and the right coset by this group, which was, I denoted G infinity earlier. You'll have to really reach back in your notes for this one. I'll remind you. So this is, remember this was the stabilizer of the zero tangle. And this group G was the stabilizer of the zero tangle. The stabilizer of the zero tangle intersect the stabilizer of the infinity tangle. The intersection of two wicket groups. Then the proposition that I think is interesting is the following. Thanks that Dave, I would say natural linear correspondence. There's natural one-to-one correspondence between double cosets of this form. Double cosets. Well, I realize I need to be a little bit careful. So, because we actually really need to do restricting application. So let's write it like this. So the double cosets we want to consider are such that, so what is beta? Beta is a grade, 2B grade, and it has the property that I described above, which is that these two links are unlinked. So these double cosets, this collection of double cosets, and what are they in bijection with? Is it clear?
Such good strike, I think.
Yeah, and B, see bridge trisections with what?
C1.
And you could filter this by putting conditions on these. For example, you could require both of these be unknowns. Maybe that would be the easiest place to start.
That's one-on-one.
Yeah. So for example, yeah. So a special case of this would be asking for these things to be unknowns. And so if we can understand which braids can be stuck in this picture to give us unknowns, then by considering double cosets of these braids of this form, we can have basically an algebraic characterization of B1 bridge trisections, which may end up being totally trivial, or maybe not. I mean, but okay, but again, if they're not trivial, then that's either mildly interesting or very interesting, right? It'd be mildly interesting if you just happen to have lots of B1 trisections of unknotted surfaces. So that would be a result about bridge trisections being very complicated relative to the topology of the surfaces. What would be better is if they were actually exotic surfaces, right? So these are the types of braids that one would want to plug into a computer, get a big list, maybe hit them with the variant, and panels paper, just like that. Okay. I have some convention about problems and exercises. Do something like this. Classify some bridge trisections. All right, so that's basically what I wanted to say about things connected to the fundamental group and classification of bridge trisections. So I think what is left to talk about is shadow diagrams and stabilization and uniqueness. So does anyone have any questions before we wade into shadow diagrams?
If you wanted to prove the unknown conjecture was true, do you have like a nice statement in terms of the stuff?
Yeah, so good question. Okay. So let's make another conjecture. Okay, so the bridge number of a surface equals, or sorry, the patch number of a surface equals the meridional rank of the fundamental group of the surface exterior. So the problem a priori is that you could have exotic surface knots that admit, bridge trisections with high patch number. Even though their groups are very simple, you're not seeing it. This is not matching. Okay. If this conjecture is true, then yeah, I'm fairly certain that having cyclic fundamental group implies the meridional rank is 1. Rank equals meridional rank for cyclic. What do you think?
I don't know. Because the meridians would be weird. Right? Well, but no. It would be 1, yeah.
It would be 1, okay.
Yeah.
Got it. I trust you. So this would tell you sort of the group is mapping onto bridge trisections in a nice way. Then if you could classify bridge trisections. And this, I think I mentioned this before, so I should have said this anyway. This is a conjecture about bridge splittings in S3, right? The meridional rank, conjecturally, the meridional rank of a knot in S3, or link, is equal to its bridge number. That's been verified for a good number of knots and links. So I think it's possible that might actually be true. This is maybe even more to ask, but who knows? And there's a little, it's not so clear. Am I asking for this to be balanced when I talk about patch number? Or am I just asking for one of the patches have this number. And for your application you have in mind, it's enough for just one of them to be 1, because then I can get my 2 tangles to be nice, and I can run my program. Good question. Anything else? Yeah, so I have this just feeling in my head that there are little things like this that I'm forgetting to mention. So anything that pops into your guys' heads, let me know. Okay. Shadow diagrams. Okay, so given a bridge trisection with its usual spine, D1, T1, we can consider, we can choose a membrane system for each tangle in the spine and consider the triple of tangle shadows on the core sigma. Okay, so just like bridge splittings of links could be studied by considering a pair of tangle shadows with the same endpoints, you can do the same thing for bridge trisections. So the definition is the following. A BC shadow diagram is a tuple, quadruple, A1, A2, A3, X, such that, well, the first condition is that X inside sigma is the standard 2B points, mark points. Makes it sound like the points are marked. I guess the points are marked. The sphere is marked with points. Each AI is a tangle shadow, and the boundary of AI is the standard mark points. And I guess the shadow, oh, yeah. Just remember they don't intersect the points anywhere. So the tangle shadow, remember, was a collection of an embedded collection of B arcs spanning the points. And then the last condition we need is that the union of any pair of these is a shadow diagram in the sense of Hagar splittings for an unlink, or for a C sub I component unlink. So this is just translating the conditions that make this a bridge trisection. And then we can say that we consider shadow diagrams up to isotopy of the AI relative to their boundary, the marked points. All right. Any questions about that definition? Hopefully this isn't too much of a surprise. So the natural proposition is that every bridge trisection can be encoded by a shadow diagram And two shadow diagrams corresponding to the same bridge trisection. I was going to say it like this. Two shadow diagrams correspond to the same bridge trisection. Only if they are jump equivalent. So, of course, what do I mean by jump equivalent? Well, I mean that, you know, the AI are jump equivalent to the AI prime, and so on. So, you know. Okay, so let's look at some examples. So let's just recall the triplane diagram for arc 2. And then, so here we've sort of suppressed sigma a little bit as this line, but for the shadow diagram, we want to sort of recover sigma as a flat region, and we want to fix our bridge points, and then, so these arcs can be flown straight down like that. These arcs can be flowed down thusly. And then the green arcs can sort of be compressed down front and back. So what does that look like? This looks like that. Okay, so this would be a shadow diagram for this guy B plus.
And that's jump equivalent to one where the blue goes the other side. It's a big blue.
Yeah, so what would a jump look like? Exactly, I could also just isolate the blue to the other side, but let's pretend we didn't do that. So we could jump blue over this, which would make it come right there. And that reflects, oh, I see, in fact, I should have done it that way. Yeah, in fact, I should have done it that way because I sort of picked the membrane that was on that side. So jumping this membrane over the smaller membrane gives me a blue curve on either side.
I was kind of wondering if there's some trick with how you draw, you know, like these half spaces are coming into a sphere in 3 different directions and having a correct orientation. Anyway. I was wondering if you take your picture up top, right? You take your tangle diagram, and then you sort of visualize a picture there.
Okay.
And then you sort of imagine the two-sphere coming out here, and then you've got front and back, and everything you figure out in that picture. And then when you superpose them all in the same two-sphere, you don't flip anything, right?
No, I don't think so.
Yeah, it wouldn't make sense to flip any one of them because then why don't you flip that one instead of the
Well,
other?
yeah, because let's just, I mean, when you do flip them, you have something like this. And so you want this to sort of be representing. So I think I did it right.
Yeah.
Now, what I thought you were asking is something about sort of sign on the points.
No.
One thing that's curious is to notice that in this example, all of the points are what we would call positive points, meaning that you can read off red, blue, and green counterclockwise.
Yeah.
And if you did this, obviously, for the other guy, you would get all negative points. And I think this is actually telling you something about positivity of self-intersections and stuff like that. Okay, so that was one little example. Oh, so one observation is that there are triangles here. So who can tell me what a triangle means?
It's a patch. No?
No, it's not a patch, but good point.
Good guess.
Because the patches are formed by pairs of colors.
Oh, that's right.
But that's a good learning moment, Dave. This is something different. This is a and actually, yeah, so this is something a little bit different. What is this triangle going to tell us in this example?
It's going to tell you if you took the surface and you just smooshed it onto the
What might we expect to show up in a shadow diagram for a projective plane? That's interesting about projective plane.
Oh, it's non-orientable.
Yeah, non-orientability, right? Because if you want to say orient this strand like that, I mean, this should also be oriented in, and this should also be oriented out, and then you get a problem right there. A triangle prescribes an orientability problem.
oh, I see.
Yep. A triangle, and as we'll see, maybe, a triangle, an embedded triangle in a shadow diagram is really actually telling you a projective plane stomach. So let's see if we can get far enough to say something like that.
Why did you need a triangle for the orientation issue? Like if I just looked.
There are other ways to have orientation problems as well. This is like the, right?
Yeah,
You don't have to have triangles if it's not orientable. You're not saying that.
So my claim is that an embedded triangle yields a RP2 summing.
I'm not an RPG summon, it's just an abstract.
Yeah, sorry, good, thank you, a P plus or minus summing. I'm not ready. Yeah, so let's see, if I draw a few more pictures, we can see that. Let's do one more example first, just to make sure everybody's on the same page. So this is the triplane diagram for the node of torus. And this is the shadow diagram corresponding to it. Okay. So exercise is to draw a shadow diagram for the sponge upwell. And I think we did this in our paper actually, so if you want, I drew one in the notes. So if you want to try to do that, then you can compare. Okay, let's see if I can get some actually interesting. Okay, so let's see if I can get an interesting example. Okay. Here are two shadow diagrams for the non-orbital surface P21. So what is C1 in these two examples? C1 is 1, and then the first one looks like this. This should probably intersect. And the second one looks like this. Okay. So maybe the observation I want to make is that, X to B union A1 union A2 union A3 is a graph. It's a graph in, immersed graph in the plane. You can, that's a graph. And so we can actually kind of think about it as and it's a graph, and it's also the spine. So the spine of a bridge trisection is also a graph. And in fact, these are cubic graphs, meaning all of the vertices have valence 3. And they're also tricolorable. In fact, they're tricolored. Okay. A bridge trisection gives us a cubic graph with 2B vertices and C1 plus C2 plus C, and 3B edges. And it comes with a tricoloring. And what's kind of cool in this case is that these graphs are different. So this one is planar. Move the screen edge out as a graph. And this one is not planar because it contains a K33 graph if you contract some edges. So that's kind of cool. So that means that this surface, the unknotted version, this surface admits 2 different 4-bridge trisections. And so I guess I'll have to save some of the other things I wanted to say about spines and graphs for next time, but maybe I'll just follow up on one thing I said before, which is if you see a triangle, and so maybe we can, if you want, you can move this edge so that it's more like this. That's more clear. So we have this triangle. And if we take a curve, which is just a push off of its neighborhood, then that is actually a reducing curve in our bridge sphere, in our chord. And so this is describing a connected sum sphere with a projected plane. And I think this one is, in fact, maybe minus this. So this is describing a connected summand with P minus. And if you remove that, that's like doing it's like cutting this out and replacing it with a single vertex where these 3 incoming edges meet. And what's left over is this K33 graph, which is exactly the graph corresponding to the unknotted torus. It's kind of interesting that the triplane diagram of the torus can be made with no crossings, but the shadow diagram is not planar.
So you really shouldn't have had greens intersecting screens here to be shadow diagrams.
Oh,
I mean, you can,
that's true.
Around it.
That's
you move
true.
them around so they intersect other colors instead.
That's right. Yeah, maybe I shouldn't have called these shadow diagrams. You're right.
You just swing it to the right.
Make it virtual cross.
But not that way. And that's actually a good point. So Peter always bugs me, like, why make them not intersect when you can always sort of push them off?
But if you really want to think geometrically, there being these membranes, the membranes.
Yeah, but somehow the shadow diagram is still well defined, even if we allow the shadows to run. Okay, well, I'm out of time, so we'll revisit this maybe in a slightly more structured way. Try it. Any questions?